Hi, you're right. So today, what we're going to be doing is learning about reflection and refraction. However, just before we do, just got a little quick announcement. I'll put this up in the post as well. So next Wednesday, you have your end of year test. Now, Miss Career has already posted on what the topics are going to be. So please go back through and have a look at what you need to be revising. Okay. However, so that's next Wednesday, the first, which is the 1st of July. Okay, so not this coming Wednesday, but the following Wednesday. So 1st of July is when your test is going to be. A couple of little things about that. Also, on the Monday, the 29th, it's quite likely that I will be in school. Um, so I might well have to just set you some revision tasks for that day. Okay, however, that's not guaranteed yet, so just keep an eye on that. Anyway, today, what we're going to be doing is learning about reflection and refraction. Now, you should have some knowledge about this from year 7 because all waves can reflect and refract as well as doing a few other things. So, what does this say? Okay, so hopefully most of you worked that out. That is ambulance. But why might it be written backwards? Okay, so have a quick think about that for a moment. Okay, so the main reason is because reflected images are essentially back to front. The scientific word you need for that is laterally inverted. Okay, inverted means upside down. So if they're laterally inverted, they're sort of back to front. So if I do this, we can see it goes back round the right way. And the reason for that is it's written backwards on the front of an ambulance because if you're looking at it through your rear view mirror when you're driving, you'll see it the right way round because you're seeing a reflected image. Okay, so today what we're going to be doing is all of you should be able to describe the rule of reflection and state the difference between specular and diffuse reflection. Most of you can accurately draw ray diagrams to show reflection and refraction, and a few of you link reflection and refraction to everyday examples. Okay, remember reflection and refraction, not the same thing, so very important there. Okay, a couple of other little things about this. Okay, this is we would have actually done this experiment in class, so I'm going to sort of talk you through how we would have done it. So, are these examples of reflection or refraction? So what I want you to do is quickly pause the video and write down, are these examples, let's move them up slightly so you can actually see, examples of reflection or refraction, okay? Up a little bit. Apologies if you can't see them all. Just move that down slightly. Okay, so you should be able to see those now. So pause the video, just write 1, 2, 3, 4, 5, 6, and is it reflection or refraction? And if you can, quickly explain why. So that'll take you no more than 2 or 3 minutes. Okay, off you go. Okay, welcome back. Number 1 is reflection. Okay, you can see really clearly the reflected image. There's someone actually taking a picture. Number 2, that is refraction. Okay, if you look at the polar bear, the top part's in the air, the bottom half is in the water, and there seems to be a weird break in the bear's body about there. That's caused by refraction. We're going to explain how that happens in a bit. This is also refraction. Okay, as we look at the wine glasses through the air and then look at them through the vase with the water in, you can see the images get distorted. This is reflection. Okay, weird kind of reflection. This is also number 6 is reflection. However, this one was a bit tricky, number 5. It is both refraction and reflection. Okay, if that was a bit of a red herring, that one there. Okay, right, so we're going to focus on reflection first because we can get through that quite quickly. So this is the experiment we would have done, and what we would have done was fix a plane mirror to a piece of paper and draw around it. Draw a normal at 90 degrees. Now remember, a normal is simply an imaginary made-up line which we use to help us measure the angles. Hopefully you remember that from year 7. Use a ray box to shine a ray on the mirror and plot the reflected, plot the incident, so the rays coming in, and the reflected rays. measure the angles of incidence and the angles of reflection. So you would have recorded your results here. Okay, so I'm going to show you an animation of what you should have seen happen during the experiment. So mirrors give us reflections. Okay, so if a beam of light is shone onto a mirror, this is what actually happens. So there's our mirror, beam of light comes in and would be reflected off. Now, the ray is reflected by the mirror, and hopefully you'll start to notice a bit of a pattern. Look at the angle that the beams of light come in at. What do you notice about the angle that they're reflected at? Okay, now if we just move that forward a bit, we can start to see. So watch closely. So, firstly, this is our normal. Okay, now the reason it's a dotted line is because it's an imaginary made up line. It doesn't really exist. We kind of just made it up to help us out. And what you would do is get a protractor and measure the angle between the incident ray, so the beam of light coming in, and the normal, so that angle there. So let's see what happens. So we measure that angle and we call that the angle of incidence. So that's a little I. And then we do the same thing on the other side, the reflected ray, that's the angle of reflection. And hopefully, if we repeat the experiment, we'll start to see what the pattern is. Okay, so the angle of incidence always equals the angle of reflection. So the first thing you need to do is pause the video now and draw this with that sentence underneath, and make it really big and clear in your books. Highlight it, bubble it, underline it. It is so vital to understanding this, because all waves do this, but we're kind of focusing on light because light is an electromagnetic wave from last lesson, but all waves do this. So pause the video, guys, copy this into your book, and then that sentence. Also, it's probably a good idea to have a little arrow on this line going that way to show that the beam of light is coming in that way, and then an arrow on this line to show it's bouncing off that way. Okay, so pause the video and do that now. Okay, welcome back. Now, the reason this happens with mirrors is because if we look at mirrors under the microscope, they are very smooth surfaces, okay? And so the beams of light bounce off them or reflect off them in a very ordered and very predictable way. However, that's not always the case with other materials, okay? So, with a mirror, the beams of light always come in like this. There they go. And they hit a flat surface and bounce off in a very predictable way because it's flat. But most surfaces, like for example a piece of paper, well, under the microscope they're not flat. They're a bit more bumpy. Okay, so if I just quickly run that back, okay, this is what we call specular reflection. Okay, so the thing that gives us a mirror image is called specular reflection, and you're going to need a description of that a bit later, but very quickly moving on. Okay, this is what happens with most other surfaces. So paper, for example, is a bit bumpy. So as the beams of light come in, what happens is this. They still reflect, but as you can see, they hit the surface and bounce off or reflect off in all directions. The beams of light are scattered. Now we still can see those beams of light, and so we still get an image, but it's not the same as a reflected image from a mirror. Okay, and we call this diffuse reflection. Okay. So we've got this image. Hopefully I've already asked you to draw that. It might be worth adding these little labels as well. So you've got your incident ray, your angle of incidence, your angle of reflection, your reflected ray, your normal, which is, remember, our imaginary made up line to help us, and your mirror. So you should already have that, but if you haven't got the diagrams, you can quickly pause it and add that. But this is a nice diagram that shows specular and diffuse reflection. So specular, the light comes in and is reflected off in all different directions, so in a predictable way. With diffuse reflection, it's scattered off in all different directions. Okay, so pause the video and just draw a very quick diagram, and then one sentence to describe the difference between specular and diffuse reflection. Okay, pause video, do that now, please. Okay, welcome back. Now, the next experiment you would have been doing was to look at refraction. Now, again, you will have done this, so hopefully this is fairly familiar to you, but what you would have been given was a glass block, and you would have been shining a beam of light from a ray box through the glass block. Now, I'm going to show you how this experiment would have worked. I'm going to get you to copy this up in a moment. I'm going to do my light in blue, just so it's really, really clear. So, my beam of light would have come in from my ray box, and just notice, so I know it's going that way, I'm just going to draw in little arrows. There they are. Now, the first thing I would have needed to have drawn in was my normal, because just like the mirror, okay, we draw a normal at 90 degrees, not to the reflective surface, but the refractive surface. Okay, so we can measure that angle of incidence just there, like that. Okay, right. So what should have happened would have been this. Your beam of light would have altered its course, like this, as it went into the glass. And then, as it came out of the glass, gone back to its original path, like that. And then just very quickly, once again, we would have drawn our normal in just at that point there. Okay, now what I would like you to do is very quickly draw that into your book. Okay, so you've got air, glass, air, and then I'm going to show you a little animation about how this works, and we're going to write then a couple of sentences to explain it. So pause the video and do that now, please. Okay, welcome back. So this is the experiment that you would have done in class. Okay, so as you put your beam of light into the glass block, you'll notice something. It's slowed down, and then as it leaves the glass block, it speeds up. I'm just going to run that back. Watch closely. Going fast in the air, slows down through the glass, speeds up again when it goes back to air. So light finds it difficult to get through glass. Now, the reason for this is because glass is denser. So think about this logically. Can light pass through air? Yes, of course it can. Can light pass through glass? Well, yes. But are glass and air the same thing? No. Glass is much heavier, much denser than air, and so therefore light finds it a little bit more difficult to get through glass than it does through air, and so it gets slowed down. So if we just watch what happens, it doesn't bend when it goes in straight along the normal. But look what happens when we change the angle, like we did with the drawing I asked you to do a minute ago. We get this bending effect. The light changes direction. So let's think about why that happens. It's been refracted, it's changed direction, but why? Okay, so the principal reason for this is the way the beam of light hits the glass block. So as light enters the glass block, if we zoom in, the whole front of the beam enters the glass at the same time. So the whole beam slows down at the same time. So therefore it goes in straight. But if we do this at an angle, something really quite unusual happens. It bends like this. Now, why does that happen? So in a moment, you're going to need to draw a close-up of this section. So let's just zoom in and think about what's happening. So I'm going to pause this. So here's the top of the beam, here's the bottom of the beam. Now look at what happens. The top of the beam hits the glass first, the bottom is still going through the air. So if I just rewind that, this part has now hit the glass. So it's slowed down, but of course this part's still in the air. The bottom of the beam is still in the air. It's going fast. So going slow, going fast. So what happens is the beam of light skews round. It's forced to change direction and go off in this direction, like that. That's why we get this bending effect, this refraction. Okay, and then of course, if we just fast forward, we can see what the effect actually is when we try it at different angles. So there's our beam of light, there's our normal. It causes our beam to bend towards the normal. If it was following its normal, sorry, if it was following its path, it would go off like this, but it's not. The beam of light bends towards the normal as it goes into a material which is more dense, like glass, and it bends back away from the normal when it goes to a less dense material, from say glass back to air. So here is what we are going to do using these words. Okay, so density, remember glass is denser and more difficult for light to get through. Density, and what else could we say? Okay, so you obviously need to have refraction in there. Density, fraction, normal needs to be in there. Okay, what I want you to do is explain why we get this bending effect. So let's just go through it one more time. As a beam of light comes in, it's transmitted through the glass, because light can travel through glass, but because glass is denser or has a greater density, it slows it down. That causes the beam of light to bend towards the normal. It changes direction. Okay, this is what we call refraction. So pause the video and then just write a couple of sentences to explain refraction in your own words. Okay, welcome back. Now, this gives rise to a couple of really cool optical illusions. I'm just going to talk you through these now. So, the first one is the appearing coin. So, if you can try this one at home, if you get a coin and put it in the bottom of a saucer, sorry, a cup and saucer like this, then if you hold it just so you can't see the coin, so the coin's at the bottom of the cup, at the moment you can't see it, so you might need to move back slightly. Then, if you add water carefully to the cup, you'll find that you can now see the coin. How does this work? Okay, so you can actually try this one for yourself at home. So, if we just have a quick look, there's the coin, but at this point, when there's no water in it, we can't see over the rim of the cup, so we can't see that the coin's there. However, if we add water to the cup, it causes the light coming off the coin, the reflected light of the coin, to refract into our observer's eyes so he can see the coin. So, first thing I'd like to do is pause the video and explain how this little experiment works. So, the reflected light coming off the coin refracts at the surface of the water, because remember, water is heavier than air, or denser than air, and it refracts into his eyes so you can now see the coin. So once again, pause the video and do that now, please. Okay, welcome back. So the next example, you can just stick a pencil in a glass. So let's see what happens with this one. Put a pencil in a glass of water and the pencil appears to bend. How does this happen? So there's our pencil. We know it's straight. It doesn't really bend at all. Rays from the pencil bend away from the normal, so where we see the tip of the pencil isn't actually where it is at all. Your eyes follow the straight line. So once again, it appears as if it's bent. Okay, so what I would like you to do is very quickly draw this and copy that into your book with an explanation. Okay, so our eyes follow the straight line, just run that back. Your eyes follow the straight line, so it seems the tip is higher up, and that's why it appears bent. So look, there it is. But that is where it appears to be. Okay, so you can quickly draw this into your book with a very brief explanation. Okay, so once again, pause the video and do that now, please. Okay, welcome back, everyone. So we've been talking about 20 minutes, and by the time you've done all your diagrams and everything, it's probably 25, 30 minutes. So just to finish off, in assignments, there are 2 YouTube videos. They're about 5 minutes in total. And then also in assignments, there is a copy of this worksheet. Okay, so what you need to do is go through task 1, task 2, task 3 on the worksheet using the information that you've got from today to help you, and then upload that through assignments. So good luck, and as always, I will be online to help you.